Hi, everyone. I'm Rong Chongzi from Peking University. I will introduce the paper named An Empirical Study of the Collapsing Problem in Semi-Supervised 2D Human Pose Estimation. Our task is semi-supervised human pose estimation, which aims to leverage large-scale unlabeled images for training the human pose estimator. Why this problem is important? The current labeled datasets used for training are relatively small and cannot cover most of real scenes. So the generalization performance of trained model is poor, especially in scenes with large changes in pose, appearance, background, and scale. Meanwhile, it is low cost to obtain large-scale unlabeled images containing person. How to effectively use unlabeled data is the key to improving the generalization ability. In semi-supervised learning, consistency regularization plays an important role. It learns from unlabeled data by requiring the model to produce the same output distribution for different augmentations. For semi-supervised classification, this method works well and achieves state-of-the-art results. However, when we apply consistency regularization to human pose estimation, it always collapses and predicts every pixel in unlabeled images as background. As shown in the figure, the response value of the heat map for unlabeled image gradually decreases with the training iterations, and the average precision is also very low. We have analyzed this collapse problem and found that it is related to the imbalanced class distribution. In human pose estimation, the class distribution of heat map is extreme imbalanced. The background pixels dominate the number of samples. When the naive consistency regularization is used, it tends to pull the predictions of different augmentation to their middle points. As a result, the decision boundary would be pushed to the area with few examples. Because the area of minor class is sparse globally, the decision boundary would pass through it and more examples would be classified as major class. To address the collapsing problem, we propose easy, a hard augmentation, which drive the less accurate predictions to the direction of more accurate predictions. For each image, it composes a pair of easy, a hard augmentations and uses the more accurate predictions on the easy image to teach the network to learn pose information of the hard one. The results show that proposed methods significantly stabilize the training and avoid the collapsing problem. The average precision increases steadily, indicating that the method successfully learned from unlabeled data. The next problem is how to construct augmentation pairs. We determine easiness and hardness of augmentation based on its effect on estimation accuracy in testing. For example, a large degree of affine transformation or masking the joint area are difficult for the model, and the testing accuracy is low. Therefore, they can be used as hard augmentation. The table shows the effect of some combinations, and it suggests that it is the accuracy gap between the two augmentations that matters. We also have tried other methods to avoid collapsing, but these attempts failed. The first is using confidence thresholding to filter the teacher signals. The second is use EMA parameters as teacher to stabilize the teacher signals. The third is class ray weighting. The final is the different combinations of easy and hard augmentations. In standard semi-supervised setting, we use COCO subset as labeled and train as unlabeled datasets, respectively. The results shows that proposed method significantly outperforms supervised method and other semi-supervised methods. When full labels are used, our approach consistently improves the performance, although the performance of the original methods is already high. There are some visualization results of our method. Thanks for your listening. For the code and pre-trained models of this work, please visit our website.